I will build a model of epidemic and clinic. Clinic, it will be a very simple discriminant model of a hospital where people are treated. Epidemic, part of the model, will be the model of people who experience a contagious disease and can potentially die if they're not treated on time. So the actual load on the clinic will depend on the epidemic dynamics, and the two models will work together, and we will see how the two paradigms are actually linked within one tool. This is the problem statement. So there's a region and there's a contagious disease in that region. All people are susceptible initially. A few are infected. Having been infected, a person for a little while, until he or she discovers symptoms, continues to live a normal life, meaning contacting other people regularly. When symptoms develop, the person stays at home and the contact rate is lower. Now, if the sick person is treated on time, then he recovers and becomes immune, temporarily immune to the disease. Otherwise, there is a probability that the person will die if he is not treated. But that probability, as we will see, is pretty low. The clinic, we'll build a very, very simple discriminant model of a clinic, finite capacity, deterministic treatment time. And these two things will interact. Some numeric parameters, just to show what kind of size of the problem we will be talking about. 2,000 people, initially 5 people are infected. Normal contact rate 5 per day, when staying for 1 per day. The survival probability is 90%, so if the person is not treated, only 10% die, 90% stay, recover. And the immunity period is from 30 to 120 days. These are the parameters. The choice of model architecture. Well, the experienced modelers will immediately identify what kind of architecture fits that problem the best way. But the choices, all choices are, we can build pure agent-based model, pure SD or pure discriminant model. We can make agent interact with SD. We can make agent interact with the process model, or system dynamics and the process model. There are other choices of architectures, and these are all practically used. For example, SD inside a person, let's say decision making inside a person is expressed as differential equations. Or a process inside an agent. Agent may be a company, a process may be a business or manufacturing process. But for our particular problem, we will choose this architecture. People will be agents, and the clinic, the treatment process, will be a discriminant model. Other possible architecture for our problem would be that one, where we will not model each person individually, but model their quantities. So there'll be the epidemic model will be system dynamics, equations, and the clinic. But clinic is clearly a process, so we will be using discriminant methodology for clinic anyway. Okay, but this is more interesting, and It's especially more interesting because you will be able to see how agent-based models are built, and what kind of, clicks and typing do I do when I build agent-based models in AnyLogic. Okay, so let's build the model from scratch. I'm prepared, so I have the same model already built. I'll put it here in case I fail to build the model in front of you. I have a chapter of our book on simulation modeling with that book will be released soon with the exact same model described step by step, and I have some notes in my notepad, so I'm all set. Okay, so new model. Epidemic and Clinic Winter Simulation Conference. I will not be using a template. So I created a new model. It's empty. I have one object here, the main object. This is the editor, the canvas of the main object. And it's empty. So I'll start with the model of the population, people. I'll go to the general palette and drop the agent population here. So our agent name will be person. The population name will be people, and let's say initially we have 2,000 people in the population. We will do animation of our model, and also our agents will be space aware, let's say. So I'll enter some area dimensions, and let's say people not contact each other really randomly, but only people contact only neighbors, let's say within the range of 30 kilometers or 30 blocks, whatever. Okay, so I have a population, I have environment that describes space and network, and as you can see here, another object appeared, person. And this is another editor for person. I think I can close all other windows not related to this model. So currently we have main and we have person, two objects, let's say. In AnyLogic models you always have main. Okay, by the way, what happens if we run the model? We have a rectangular space and 2,000 people doing nothing. I can open any object in AnyLogic and see that it's just animation. There's no behavior, nothing inside the person, and no events, nothing happens in the model.
So, good question.
Sorry, yeah?
Since for every agent you had a width and another dimension, and they are crowded, so that means the main area you have defined, how big the main area is? Or
yeah, I just define it. It's 650 by 200, whatever, kilometers, whatever. It's you are free to define any kind of areas, or you can do agents in 2D or 3D. In my case, this is just a geographical space, so I'm using a 2D, two-dimensional space for agents. Okay, now I'm inside the person, and I'm about to define the behavior of a person. And I'll open the state chart palette. Now, anybody in this room is familiar with state charts? A few. Okay, I can say that state charts is the most useful language to define behavior let's say, event and time-driven behavior of agents in agent-based modeling. State charts are coming from computer science, namely from concurrent systems and different languages, model languages, like unified model language. But they turned out to be extremely useful in agent-based modeling. So I will use a state chart to define the behavior of our person. So initially, all people are susceptible to the disease. So there's state susceptible. After people are infected, but don't see symptoms, they are in a state which I will call exposed. This is the terminology from the epidemiology science. When symptoms are obvious, people stay at home, and that stage of the disease is called, well, we'll call it, okay, let's call it infected. This is, again, the standard term. Initial state is susceptible. This is the initial state marker. There is a transition from susceptible to exposed, transition from exposed to infected, and then two things may happen. First of all, the person can be treated in a hospital, and then the person goes into recovered state. If he is not treated in a hospital, then there are options. And we will use this transition branch here. Option 1, he still recovers. Option 2, the person dies. This is the final state. This is, I'd say, not treated. This is treated in a hospital. Survived. And died, or death. Okay. Now, I'll add some parameters to the model. I could use directly the numeric values, but just to show you that you can, how you create parameters, I'll create parameters for a couple of things. Let's say for contact rates and for infectivity. This is a parameter. Contact rate is 5 per day. And contact rate symptoms is 1 per day. Infectivity is the probability that another person contacted by a sick person will get infected. Is, as far as I remember, 7%. Yes, correct. And last parameter is survival probability. It's 90%. Okay. note that those parameters are located within the person editor, which means that they are local to each agent and they can be set up individually and differently for different agents. Alternatively, if I think that these are global parameters of the model, I could place them in the main object. You can treat main as environment where agents live. Okay, now, what triggers the infection transition? Someone else passing infection to that person. We will, in our modeling language, we will model that as a message. So the transition is triggered by the message, and message should equal, let's say, we can use just the text string infection. So this transition is triggered by a message explicitly sent to this particular object. While the person is exposed, he is in incubation period. An incubation period has a certain duration. So the transition symptoms is clearly triggered by time, it's timeout. And let's see how big is this timeout. The incubation period is uniformly distributed between 1.5 and 6 days. So I'll enter here. I know the name of the function, but what if I don't know the name of the function, or I roughly know the name of the function? I can use what's called code completion. I press Control space, then AnyLogic gives me suggestions on what can I type, so I don't need to remember the exact names of variables and functions there. So there's uniform from minimum to maximum. And I'll use uniform from, again, 1.5 and 6. Of course, assuming the time unit is day. All right. Now, treated. Treated means the person has been treated in a hospital. We don't have a hospital model yet. But certainly there'll be a technically, let's say, an interaction between the person and the hospital. And we will model this as another type of message sent to the person. And I'll say this message is treated. If not treated, we're letting the disease progress in its natural way. And we know that the illness duration, if not treated, is from 10 to 40 days. So I'll enter another uniform distribution here from 10 to 40. And the survival probability is 90%. So I'll use the function random true, which will give the true result with this probability. This is one of the built-in functions in AnyLogic. Otherwise, the person will follow that way. So with 90% probability, having come to this decision diamond, the person will recover. Otherwise, he will die. Okay, how do we animate all this? Or how do we debug all that? One of the things we can do, we can basically paint the person animation with different colors. So I'll use different colors for states. Susceptible, infected is red, and then recovered is green. And I'll paint the default animation of person with different colors depending on the state. So I'll go into the susceptible state and say person. Person is the name of this shape. Dot set field color. I know I have a set function. Gold. Now, AnyLogic is completely open at Java level, and in AnyLogic there are no other scripting or textual languages other than Java. It does not mean you need to learn the full object-oriented programming to use AnyLogic, but it does mean you at least need to learn the syntax of simple statements and expressions, like what I'm doing here. Right now I'm doing pretty regular agent-based modeling in AnyLogic. So those kind of the language construct of that kind of complexity are pretty usual in agent-based modeling. So I'll just copy that into every state. Dark orange. Red. And yellow-green. Now, what is entry action? Entry action is the action that is executed when the state chart enters that particular state. Okay? Now, let's run the model again. Okay, so everybody is yellow. So we know that most probably everybody is in a susceptible state. We can check that. So, okay, this guy is in susceptible state. The guy number 4 is in susceptible state. The guy number 1000 is in susceptible state, etc. But nothing is happening. Nobody has a disease. Why is that?
Excuse me, do we, does each agent need something like a sensor? When, you know, an agent will send a message, but when will it send a message?
Exactly. That's a very good remark, because we haven't yet programmed this. Yeah. Okay. So far, the model is doing nothing. Everybody is in susceptible state, and nobody gets infected because we haven't yet, you know, defined the initial infection, right? So let's do it. What I'll do, there's a number of ways we can infect initially some people. I'll bring a button to here, to the main. I'll call it infect 5 people. And I'll do this. People, random, send infection, I think. Yes. Or alternatively, I could write a loop. Just leave one statement like this and say that it needs to be executed 5 times.
Excuse me.
Yes?
If I want to reference a Java class there instead of writing code, is it possible?
You reference a Java class? You mean external Java class? Of course. Of course. AnyLogic allows you to create your own Java classes, or to use jar files and classes external to the model. So yes, definitely. Okay, so I corrected the error, and let's run the model again. So you see, there are several people, 5 people are currently sick, but they do not infect others. And they do not infect others because we haven't yet programmed that part of the people behavior.
But in theory, this way you would infect the same person twice, right?
Correct.
So,
Because the random is truly random. So there is a probability that one person will be infected 5 times. It's a low probability, yes. But this is just, you know, a demo model, so we don't care too much about this. So the interesting thing is how people contact each other. They contact each other all the time, but we're only interested in contacts done by people, exactly, who are infected. So who are in exposed state and in infected state, right? So we will, this behavior, and we will just model those kind of contacts. So I'll open the state chart again, and I'll do what is called internal transition. That transition contact exposed. That transition will happen at a certain rate, and rate is contact rate. This is normal contact rate while a person has not yet discovered symptoms. And I will do this here. I'll use the function send. Message to other agent. So I'll send infection to a random connected agent. And I could leave it that way, but the thing that will happen, that we will, every contact will result in infection being passed. So I'll do one thing. I will only model those contacts that result in infection being passed. So I'll multiply the contact rate with infectivity. So only 7% of my contacts will be explicitly modeled, and each contact will result in infection being passed. So I'll lower the contact rate, only modeling 7% of contacts, which is also computationally more efficient, and I'm sending the message infection to a randomly connected person. Okay? Same here. This is contact while infectious. But the only difference here is that the contact rate is lower, the base contact rate. Contact rate symptoms. Let's try this. Okay, so we see that the disease is being passed, and now the model reaches the stable state. Nothing wrong. I'll just ran the model in the fast way, and it finished because there are no more events are happening. Who are those people? The red people are actually dead people, but they're still present in this picture because we haven't explicitly deleted them from the model. And why people are, while the epidemic does not, progress further, just because we haven't modeled the loss of immunity. And these are the two things that will add to the model of the person, which is almost finished now. So, first of all, I'll go to the dead state and say, I want to delete myself from the model when I'm dead. So, here I will use this get main, remove people, this. In Java, in AnyLogic, this means this particular object. So we are inside person, we're removing this person from the model. This is one thing that was missing. The other thing is immunity loss. Who knows how do I model immunity loss, given that we're using state charts for behavior definition?
We have a timeout condition when we go back to the how's it called? Susceptible.
Susceptible, yes.
Yeah.
So what do I need to add? A transition from recovered to susceptible. Exactly. So that's what I'll do. Transition, yeah. From here to there. I will call this transition immunity lost, and that transition will be triggered by what? Time. So the immunity period is from 30 to 120 days. I'm using uniform distribution, but I could use really any of the about 40 distributions embedded into AnyLogic, triangular, normal, etc., etc. So there's a whole lot of different distributions in there. So uniform again from 30 to 120. That's it. And also I will say that my model will be maximized size, so I don't have to resize the window all the time. Okay, nobody is infected. Why do we have this kind of oscillation here? Because well, the model is essentially stochastic, of course, right? Because the illness duration, the incubation period, and immunity period are all stochastic variables. And we did observe oscillation because by the time somebody loses the immunity, somebody from the previous wave of the epidemic can infect him, right? So you see that this is again stochastic agent-based model. So right now, people, well, the epidemic, even without a clinic, it's ended. But very few people are left in the model.